Hello everyone, I'm Stavros Keppas, Head of Weather Research and Development and Meteorologist here at WeatherXM. With the ongoing curiosity surrounding the inner workings of the Weather R&D department, I find it a great idea to take some time and dive into the core projects that we are currently engaged in. In this video, we will provide an overview of our main weather projects, highlighting their significance. Specifically, we will briefly discuss our innovative cell capacity model. We will give an overview of the current quality of data mechanism, the so-called QOD and its future steps. We will have a look at the quality of forecast, what we call QOF mechanism, and we'll introduce our latest development, which we call the Mosaic Forecast. Before we move into the specifics of our projects, I would like to introduce to you some fundamental knowledge and concepts to understand the importance of reliable weather data. So one of our primary objectives is to enhance weather forecasting. However, to appreciate how we achieve and improve weather forecast, let's first understand the process of weather forecasting. Currently, there are two main approaches. A timeless statement that I really like about weather models is that the latter atmospheric conditions are driven by the previous ones. So we need accurate physical laws and accurate observations of the current state of the atmosphere as an input, but we know that both are still not so accurate even today. So the process in a traditional forecast production is we collect observations around the world, we introduce them into a model, and then prognostic and diagnostic equations are solved, simulating processes that take place in the atmosphere and between the Earth's surface and the atmosphere. So if we need to improve a forecast, we firstly need to improve physics in the quality and the representativeness of the data that we introduced into the model. The other way that is kind of a trend nowadays is to use machine learning models to detect patterns of parameters forecasted by traditional numerical models and then estimate the future by correcting the initial forecast produced by a traditional model. Here we need to train our machine learning model with historical data of both forecast and observations and find relationships between them. In both cases, the common denominator is the need for high quality weather data. Hence, no matter the way that you do it, the basic substance on the way to a better forecast is providing good data to a model. Because erroneous data lead to erroneous weather forecasts. In fact, as a simple illustration, even a small error of 0.5 degrees Celsius in the input temperature, so in the temperature measurement that we introduce into a traditional numerical prediction model, could lead to a much different forecast 5 days ahead or even earlier. Here you can see a typical ensemble forecast graph showing 2-meter temperature forecast produced by different sub-models of the European Center for 7 days ahead. Note that while temperature deviations are small at the beginning, they finally end to huge differences, even larger than 10 degrees Celsius, 5 to 6 days ahead. And in the end, both erroneous weather data and erroneous weather forecasts lead to wrong decisions. And this is one of the problems that we try to fix here. Given an example, a 20-year time series of precipitation full of errors or non-representative historical data for a region will lead to wrong planning of infrastructure. Example given, construction of a non-durable bridge against floods or strong winds. On the other hand, an inaccurate forecast which does not warn for hailstorms leads to taking no precautions for protecting a field of cherry trees, for example, and eventually a hailstorm will be disastrous for the crop and the local economy. So it seems that qualitative data are more than essential, and this is for a series of reasons. We need qualitative data to feed weather models, but we need both accurate weather observations and forecasts to facilitate the pillars of regional and global economy, such as agriculture, energy, and infrastructure development. As a matter of fact, historical weather data help us planning economies, while weather forecasts assist in protecting economies. Today, there are several weather networks providing weather data across the globe. Just a few of them, though, are certified and follow general quality guidelines. But speaking as a researcher, in general, there are no networks that someone can trust at first sight. In addition, if someone needs data across the world, he needs to search for several institutions and then merge data to construct a complete dataset, and there is also an inconsistency between all these datasets. WeatherXM tries to create a united network of weather stations where we always know which stations are reliable or not, and even which data points of a dataset may be problematic or not. To achieve this, we rely on our community, which facilitates the deployment of weather stations across the world. Then we reward our users for deploying and maintaining their station well, and eventually providing us qualitative data. And finally, this data can be provided to stakeholders. And that's the way that we create a cyclic economy where the network token is distributed to station owners for the data that they provide, who can actually convert tokens to money or services. Then enterprises buy token to use data and services, and thus money returns to the network. In such a way, we are creating the first decentralized global weather network, and till today we have a growing network of 5,000 weather stations on the planet in less than 3 years, and a community of more than 9,000 members. And now let's get deeper into our mechanisms, showing how do we process all this weather data. The first question here is, how do we ensure the quality of data? There are 3 steps to achieve this. First, we use a reward mechanism to ensure either the expansion but also the good operation of our network. So a user will get rewarded if the weather station is well deployed and well maintained. Then we want to distribute the weather stations in a scientifically reasonable way and represent Earth's climate in the best possible way. And finally, we make all the appropriate checks to ensure that the weather data we collect are of good quality. Actually, this is associated with the reward mechanism, so the quality of data mechanism regulates both the rewards that we give to our users, but also denotes the value of the data. So for someone that has not already been a member of growing community, there are 3 simple steps to do it. First, you need to get a weather station. Second, you need to ensure that the station is deployed and works properly according to our guidelines. And if the 2 previous steps are satisfied, the user is rewarded in WXM tokens. Now let's move to our unique cell capacity model for a while and get a broad idea of it. The real and very tough question here that we tried to answer was how representative a weather station can be. But this is not an easy to answer question, especially when you try to estimate the representativeness for every single region of an entire planet. To tackle this problem, we employed meteorology, topography, and land use of areas. So we need reasonable meteorological criteria to ensure that phenomena like sea breeze, which has a significant impact on the microclimate of the coastal areas, temperature inversion that may be hazardous for agriculture, and small-scale precipitation like showers and thunderstorms that play an important role in hydrological cycle, energy production, and agriculture insurance are observed. Then we also need topography to detect and determine the orientation of mountain slopes, which are affected differently by weather systems. And finally, we need land use to distinguish dense urban areas from parks, rural and coastal areas, which are characterized by different microclimates. So what we finally produce is a high precision map with zones of representativeness. In order to understand this, let's make it a picture. In the case of the highly populated city of Istanbul in Turkey, for example, if we get a large picture, we can definitely detect hexagons that are dominated by urban areas with grey or by rural areas with brown. If we zoom into some cells, we could see that, for example, a coastal waterfront requires a weather station, while another one is needed for the highest point of an area. If this fulfills our topography and meteorology requirements, then the differently orientated slopes need one station each. Also, large urban agglomeration needs one more weather station, a large park needs one more, and surrounding areas need an extra station. Having finally developed this model and having applied it on minimum and maximum requirements suggested by WMO and the scientific community, we're able to estimate that the number of weather stations required on a global scale are 1.1 to 36 million stations using minimum or strict criteria respectively. In other words, we strive for a density of stations between 1 station per 136 square kilometers to 1 station per 4.2 square kilometers. And if this number sounds outrageous, there is a great body of scientific evidence that shows that the required density for urban areas or areas of complex topography is even less than 1 square kilometer. The methodology is open source and it can be found on GitHub, while there is a full documentation which can be accessed through our post on Medium. Now let's move to the next weather project, which is the QOD, or Quality of Data Mechanism. So QOD is one of the links in the chain of the reward mechanism. In order to be able to trust the data of a station, the data needs to pass through different checkpoints that are part of the reward mechanism. First of all, it's crucial to ensure the location of the weather station. This ensures the seamless linkage of time series data with specific geographic coordinates. It's worth noting that an extended time series holds significant value not only for forecasting but also for characterizing the microclimate of a given area. The next and very important step is QOD, which is responsible for the quality of data and the identification of the deployment status of a station. Then we will deploy the cell capacity model to ensure that weather stations are properly distributed across the globe, being representative for the climate and weather of the area where they are deployed. And as a future step, we aim to classify weather station hardware based on the parameters they can observe, as well as their overall quality and specifications. This classification will aid in selecting the most suitable stations for specific monitoring purposes and ensure optimal data collection. All these mechanisms will finally lead to rewarding a user. At this moment, our users are experiencing the version 1.0 of our QOD mechanism. This version practically annotates every single package of data that is sent by a weather station, and the basic processes taking place in this version are: first, we check for values which are out of the bounds that the sensor can measure. As an example, if temperature sensor is able to measure till 60 degrees Celsius and there is a record of 90 degrees Celsius, then this is considered as a faulty measurement. Second, we identify suspicious spikes across different temporal levels to detect sensor faults or bad deployments based on WMO criteria. For example, a temperature change of larger than 3 degrees Celsius within a minute is considered as suspicious given the usual rate of temperature fluctuation. Third, we verify if the expected data packages were received at the anticipated intervals. This aspect is particularly vital for maintaining a consistent sampling rate, especially for capturing small-scale temporal phenomena. Currently, we aim to receive a minimum of 60 data packages per minute from an M5 weather station and 18 data packages from a helium weather station in accordance with WMO regulations. And fourth, we check the constancy of data based on WMO criteria and our data analysis as well. For instance, we check if temperature remains constant for extended periods of time. This checkpoint is really important as it enables us to check for possibly bad deployments. Here the most sensitive parameter is the wind. And as there were many users that got messages on their mobile screens that the wind speed is constant, I would like to say a few words here. In general, wind speed can indeed be constantly at 0 meters per second for hours if relative humidity is very high, as calm conditions is one of the criteria for the fog formation, for example. However, in all the other cases, we expect at least a single gust of wind larger than 0 meters per second within a couple of hours or something, and it would be very unlikely if this wouldn't happen. While QOD version 1.0 represents the current state of our quality assurance efforts, Our journey towards ensuring data quality extends far beyond this version. This is only one of many stones to build the QD wall against faulty measurements and deployments. Our next step is called Indoor Station Detector, or ISD, and it will be the new feature of QD version 1.1. This feature will be able to distinguish between indoors and outdoors weather stations. This is the main feature, but we also aim to detect very bad deployments and problematic illuminance sensors by comparing observed and theoretical illuminance together with a few other meteorological parameters. This feature is already developed and being tested. In our upcoming release, version 1.2, we're introducing a new feature called the Solar Obstacle Detector, or SOD. This innovative process utilizes solar irradiance to identify significant obstacles around the weather station. Currently, SOD is still in the research phase, but we anticipate it will serve as an additional tool for users, encouraging them to improve their deployment setups. Following version 1.2, our most challenging and crucial step will be version 1.3. This version aims to compare our weather stations with reliable stations or other data sources which may originate from our network or third-party networks. However, this step presents numerous challenges and difficulties that we are actively working to overcome. To facilitate the entire QD mechanism, we are planning, in addition, to implement an additional process for collecting and evaluating photos of weather station deployments. At WeatherXM, we place a strong emphasis on quality, which is why we dedicate extensive time to various sub-projects related to quality of data. Ensuring the reliability of weather data is an essential, as it enables us to deliver dependable weather services and fulfill our ambitious goals. One such goal is to become the first company capable of evaluating all available weather forecasts worldwide in real time. By leveraging the ground truth data provided by our stations and identifying reliable sources, we can confidently assess weather forecasts. This in turn allows us to develop our own weather forecast models based on the high quality data we produce. Coming to the end of this video, let's have a look at one of our attempts to produce an improved and customized forecast for each of the locations that the weather station has been deployed. The first process towards what we call Mosaic Forecast is the quality of forecast, or the so-called QoF mechanism. The QoF mechanism is a process that evaluates all the available weather models and finds which one performs the best for each location of the world. As models can be updated from time to time, and also the average atmospheric circulation is different from a month to another, we run the QoF mechanism for a certain time window in the past, for example the last 15 to 60 days, and we find the best performing model for each forecast day ahead. Here's how it works. We gather weather forecasts from different models for each day over a designated period, example given, as we said, the previous 30 days for example. Keep in mind that a model produces forecasts for X days ahead. Next, we determine which model exhibits the best performance for each of the 6 days ahead that we aim to forecast. And finally, we compile a 6-day mosaic of forecasts sourced from various models, producing a much more reliable forecast tailored to specific features of a certain location. Here we present a comparison example showing the performance of our 4-day ahead mosaic forecast for temperature against observations from a weather station in Istanbul in Turkey and forecasts from other global weather models. And we can definitely notice that the temperature of the mosaic forecast is very close to our ground truth. In addition to this single graph, our first analysis of the results reveals that the mosaic forecast outperforms others, demonstrating promising results across various locations worldwide. Concluding this presentation, as a meteorologist, I strongly believe that this project represents a revolution in meteorology, reshaping how we perceive weather data and formulate forecasts. In an era driven by data, we definitely need data of high quality, and our mission at WeatherXM is to ensure the production and provision of clean, reliable and qualitative weather and climate data. That concludes our presentation for now. Stay tuned for our future updates on weather projects. Until then, take care and see you soon. Bye bye.